Since word problems can be tricky, I think I'll do just one more. I really kind of like the algebra in this one anyways. So we have a function, and what we're imagining is we have some circular ring of wire. Its radius is r naught, and it's lying perpendicular to the x-axis. That's kind of funny to say in 3D. Okay, so here's what I'm picturing. It's like the x-axis runs right through the middle of it. So here's the x-axis running into our circle. Hopefully that makes sense. Okay, so this is x. Centered at the origin, so this is happening right when x equals 0. So this is just floating around the x-axis. It has a positive charge spread uniformly over it, and we have a formula that tells us the electric field in the x direction at point x on the x-axis. So if we're out here at some x coordinate and we plug that into this function, it will give us the strength of the electric field. But once again, we have this constant k in the mix, so we're supposed to be thinking about this as E as a function of x. So actually we have two of them. We have this k that we should be assuming is constant, and we're given a little information it's positive. And then we have this r naught, which is the radius of the circle, which should be constant as well. You could vary the radius of the circle and look what's happening, but since we're told to consider x to be the thing that's determining the field, I would assume that that's constant. For now, we need at least, we need only one of them to be changing. We need everything else to be constant. Okay, so we want to figure out at what point the field is greatest. So we're looking for the x value that makes the field greatest. So we're not given any cutoffs, so we're going to need to do negative infinity and infinity. And then we'll need to check any critical values. We don't have endpoints, but we can check for critical values. So we're going to do a derivative. And this is a quotient, so it's going to be a quotient rule. So we'll get this x squared plus r naught squared raised to the 3/2, there's our bottom, times the derivative of the top. So this is constant times x. The derivative of that will just be constant times 1. And then we want minus the top, kx, times the derivative of the bottom, which is going to be a power rule, 3/2 x squared plus r naught squared to the 1/2. And then there's a chain rule there as well. The derivative of that inner stuff, x squared plus r naught squared, is going to be a 2x. We're assuming r naught squared is constant, so its derivative is 0. And then that should be all over x squared plus r naught squared to the 3/2 and then squared, which will be 2/3. Okay. And we want to know when this is 0, when it's undefined. The undefined part, the answer is never. This is something that has to be positive. Well, okay, let me think about this carefully. If x is 0 and r naught is 0, then the bottom is 0 and we're in trouble. But I think it's okay for us to assume that r naught is not 0, because then we won't have our circle. So assuming that r naught is positive, this will be positive, and this at smallest is 0. So the bottom is never 0. Okay, so let's see. I'm trying to think. There's a couple of different ways to think about this. One is just think about it as factoring. Oh, hold on, I spotted some things I want to do first. I am seeing that there's a 2 that cancels out. Maybe that's all I want to do. So you could either think about this as factor to deal with these fractional powers, or you could think about it as multiply top and bottom by an x squared plus r naught squared to the 1/2, and that deals with them. I'm going to show you the factor, but keep that as an option if you hate it. So I want to separate out an x squared plus r naught squared. These both have x squared plus r naught squareds in them. There's a 1/2 of 1 in here and 1.5 in here, so I'm going to take out 1/2 of 1. And then I'm going to factor out a k as well. And I think that's all I can get. So the tricky part, but it's really just exponent rules, is if you divide out one of these to the 1/2 from this thing to the 3/2, 3/2 minus 1/2 is 1, so you're actually just left with an x squared plus r naught squared. So if you need kind of a side example for that, it would be like saying I have a to the 3/2 odds over a to the 1/2, and you'd subtract powers. Okay, so that's from this first chunk. And then I took the k, I took this out, so I have an x and a 3 and an x left over, so it's minus 3x squared. Okay, and then you can actually simplify this a little if you want. There's more than one way to do it. One is to say if I'm going to get rid of this to the 1/2, that would knock this down to the 2.5. So maybe I'll do that, but it doesn't really matter if you don't. And then I have an r0 squared minus 2x squared. Again, what I'm saying there is if I cancel one of them out, it's like dividing it out of the top and the bottom, so it's gone from the top. When I knock out a square root of this from the third power, it leaves me 2.5. Okay, and we wanted this to be equal to 0. K is positive, so that's not going to do it. The bottom doesn't contribute, so I need my r0 squared minus 2x squared to equal 0. Which means my r0 squared equals 2x squared, and I'm trying to find the x value that gives me the greatest field. So I'm going to divide by 2, and then I'm going to square root both sides. Okay, and then you could leave it there, but I'm actually going to go one step further. If I take the square root of r0 squared, I get technically the absolute value of r0 because the square gets rid of any negative signs. But r0 is positive anyways, so we'll just say it's r0 over the square root of 2. Okay, so those are the critical values. Which means, back up here, I need to check e of negative r0 over the square root of 2. That's legible. And r0 over the square root of 2. Okay, so this, I didn't leave myself very good room, so we'll scratch work it right here. So if I want to find e of negative r0 over 2, square root of 2, so I'm going to plug that in, so I'm going to get k times negative r0 over 2, and then I'm going to get, so this is my x, right? So I'm going to get that thing squared, which is going to make it positive r0 squared over 2 plus r0 squared to the 3/2. All we need to be able to do here really, in fact I'm getting ahead of myself because I know things. So let's just see if we can simplify a little bit. Okay, so negative k r0 over 2. In here I have 1/2 r0 squared plus r0 squared, so that's 3/2 r0 squared to the 3/2. I'm just going to quit there for now. Really similar, in fact, is it identical? Not quite. When you do positive r0 over the square root of 2, that's k times positive r0 over 2 in the top, and then the bottom is exactly the same because it was squared, right? So we have an x squared plus r0 squared, and when we square this, we once again get r0 squared over 2. Square roots of 2. Sorry. Square roots of 2. Plus an r0 squared, so it's going to be 3/2 again, and then to the 3/2. So really similar work, it's just the top doesn't have the negative sign this time. Okay, so that's something. Let's look at what happens as x goes to plus or minus infinity. So as x gets really, really big, the k becomes pretty negligible, as does the r0 squared. So in the bottom, it's in the ballpark of x, big number squared to the 3/2, which is like big number cubed. So this is going to behave like big number cubed in the bottom, and just our big number in the top, which is going to be acting something like, 1 over x squared. When x is a really big negative number, that thing's really close to 0. And when x is a really big positive number, it's really close to 0. So the field is tapering off as we get further and further out, which makes sense to me, in my limited knowledge of fields. So the critical values are definitely what we're interested in, and really all it takes is for one to be positive or negative for it to beat out 0. So looking back at this, remember it was really important that we paid attention. We assumed k0 and r are both positive, So here we have negative, positive, 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 so a negative top, and the bottom is always positive. Here we have positive top and always positive. So this is the value we get, but what we really care about is that this one, okay, so this is going to be a min, and this is going to be a max. I don't really care about the value of the min or max, but just to say that the field is greatest at, see, this is a funny one. I'm guessing here that the negative is just because there's a direction associated with it, so really the field is the same size at these 2 points, just going a different direction. So I think technically the answer is the field is greatest at plus or minus r naught over the square root of 2, but again, the calculus version, if we're not really thinking about that or sure about it, we could just pick the positive one. I would take that for sure, say that's greatest. So I'm going to say the bottom one because that really sounds right to me, but again, I wouldn't penalize you for not realizing that maybe the negative was just a direction and really meant the same thing. So that is my answer. So I think my heads up on these are just to make sure that you don't just stop at finding critical values. I need to see this work where you make sure that it's really a max.